Scientists just did something that was once considered completely impossible. They took a photograph of another planet in another solar system. Not a drawing, not an artist's impression, not a computer simulation. An actual real photograph of a world that exists 111 light-years away from where you're sitting right now. When you understand what it took to get that image and what it actually means for the future of humanity, your brain is going to struggle to fully process it. Because this is not just a space story. This is the beginning of something that every generation before us could only dream about. Stay with me because by the end of this video, the way you think about the universe is going to be permanently different. Let's start with something that will immediately put this into perspective. Right now, as you're watching this, there are over 5,900 confirmed planets outside our solar system. 5,900 worlds that we know exist. Planets bigger than Jupiter, smaller than Earth, some made of rock, some made of gas, some orbiting two stars at once like something straight out of a science fiction movie. We know they're out there. Scientists have spent decades proving it. But here is the insane part. Of all those thousands of planets, almost none of them have ever been directly photographed. Not even close to directly photographed. Scientists mostly found these planets the same way you would find a lamp post in a pitch-black room by watching someone walk in front of it and noticing the light flicker. That is basically the science. You look at a star, you wait, and if the star briefly dims for a moment, you know something passed in front of it. That is how the majority of known exoplanets were found through a shadow, a tiny momentary dimming of starlight. That is it. For decades, that was the best humanity could do. And that is what makes what just happened so jaw-dropping. The James Webb Space Telescope did not detect a shadow. It did not watch a star flicker. It literally took a picture of the planet itself, an actual photograph. A real image of a world orbiting a different star. And not just any world. This is now the lightest, smallest exoplanet ever to be directly captured in a photograph. That record has stood until right now. Webb just smashed it completely. The planet is called TWA-7b, and it orbits a young red dwarf star known as TWA-7, also called CE Antlia, sitting approximately 111 light-years from Earth in a constellation called Antlia. Now, 111 light-years sounds enormous, and by human standards it absolutely is. But in galactic terms, this is our cosmic backyard. It is practically next door. The universe is 13 billion light-years across. We're talking about a neighborhood that is, cosmically speaking, practically attached to our front porch. The star itself, TWA-7, is remarkably young, only about 6.5 million years old. For comparison, our Sun is 4.5 billion years old. TWA-7 is so young that in cosmic terms, it is basically a newborn, still surrounded by a massive swirling disk of dust and debris, the leftover raw material from the planet-forming process. Scientists have known about this star and its debris disk for years. They could see 3 distinct ring structures within that disk when they looked at it with ground-based telescopes, 3 rings of dust and rocky material separated by gaps. And those gaps were a huge clue because in planetary science, gaps in a debris disk almost always mean one thing. Something is there, something with enough gravitational pull to clear out the material around it and carve a lane through the disk, like a planet-sized cosmic lawnmower cutting a circle through the dust. For years, astronomers suspected a hidden planet was responsible for the structure of that disk. They just could not see it, not because it was not there, but because finding a planet inside a debris disk while it orbits a star is one of the hardest things in all of science. Think about the problem this way. Imagine you're standing far away trying to spot a firefly that is hovering right next to a searchlight. The searchlight is blasting so much light in every direction that the tiny glow of the firefly is completely invisible. That is the challenge. Stars are unimaginably bright. And next to its star is so much dimmer that trying to photograph it directly is like trying to spot a birthday candle sitting next to the surface of the sun. The star just drowns everything out. This is the reason direct imaging of exoplanets was, for most of human history, essentially impossible. And this is exactly why what Webb just did is such a massive deal. Here is how they did it. The James Webb Space Telescope is equipped with something called a coronagraph. It is built into an instrument called MIRI, the mid-infrared instrument. And this piece of technology is genuinely extraordinary. A coronagraph is essentially a high-tech star blocker. It is a precisely engineered optical device that sits inside the telescope and physically blocks out the light from a target star, like putting your thumb over a flashlight so you can see what is behind it. But this is not a simple thumb. This is an engineering masterpiece. The coronagraph on Webb uses something called a four-quadrant phase mask, which splits the incoming light into 4 sections and cancels out the starlight through destructive interference. It is optical wizardry at a level that takes years of physics training to fully understand. And it works so well that it can suppress the blinding light of a star to the point where the faint glow of a planet orbiting that star becomes detectable. But even with the coronagraph doing its job, some starlight still bleeds through. It always does. This is where the image processing comes in. After Webb captured its raw data, a team of scientists led by Dr. and Marie Lagrange, an astrophysicist from the French National Center for Scientific Research in Paris, ran that data through advanced image processing algorithms that further subtracted and removed the remaining stellar glare. Layer by layer, they stripped away the noise. They removed the star's contaminating light mathematically. And when they did, sitting there in the data, in the gap between the first and second ring of the debris disk around TWA7, was a faint but clear infrared source. Something was there. Something that was not supposed to be there if there were no planet. Webb first stared at the TWA7 system back in June 2024. That first look revealed the faint object sitting right where the gap in the disk was. But the team was careful. Science requires caution. Could it be a background galaxy? Could it be something unrelated to the star system that just happened to be in the field of view at the right angle? They calculated the odds. The probability that the infrared source was a background galaxy rather than a planet was about 0.34%. Less than 1/3 of 1%. The evidence was overwhelming. What they were seeing was almost certainly a planet. Their findings were published on June 25, 2025 in the prestigious scientific journal Nature. And the world of astronomy was immediately electric. Now, let us talk about what this planet actually is. Because TWA7b is genuinely fascinating in its own right, not just as a discovery but as an object. The planet has an estimated mass of around 100 times the mass of Earth, which works out to roughly 0.3 times the mass of Jupiter. In simpler terms, it is roughly similar in mass to Saturn. That makes it a gas planet, not a rocky world. And it is not the kind of place you would want to visit. But the mass is actually the most important number here because of what it represents in the history of direct imaging. Every single exoplanet that had ever been directly photographed before TWA7b was significantly heavier than this. The previous record holder was 10 times more massive. 10 times. TWA7b is 10 times lighter than any exoplanet that has ever been directly imaged in the history of astronomy. This is not a small improvement. This is a completely new category of planet that we can now see with our own instruments. The planet sits roughly 50 times the distance of Earth from the Sun away from its host star. In our solar system, that would put it somewhere beyond Neptune, out in the cold and distant outer reaches. And cold is the right word. Initial analysis suggests that TWA7b has a temperature of around 320 Kelvin, which works out to roughly 47 degrees Celsius, or about 117 degrees Fahrenheit. That sounds warm, but for a planet still glowing with the heat of its own formation, it is actually quite cold. It is a young planet, still fresh, still radiating the heat from its own birth in the dust and gas that surrounded its star millions of years ago. It is like a planet caught in the act of growing up. And here is something that makes this discovery even more scientifically important. This is the first time a planet has ever been directly seen inside a debris disk. Astronomers have long theorized that the ring structures and gaps in debris disks are created by planets clearing those gaps gravitationally. It is a cornerstone of planetary formation theory, but it had never been directly confirmed. Nobody had ever looked at a gap in a debris disk and then also seen the planet sitting right there in that gap, proving the connection. Until now, TWA7b sits exactly where a planet of its mass should sit to explain the structure of the TWA7 debris disk. Its position matches the gap perfectly. This is direct observational confirmation of how planets shape the disks around their stars. This is planetary science being proven in real time. There's also another intriguing possibility that scientists are investigating. The data from Webb suggests there might be a small collection of dust trapped in TWA-7b's orbit, sharing the same orbital path as the planet itself. In our solar system, we call these Trojan clouds. Jupiter has enormous groups of asteroids, the Trojan asteroids, that share its orbit and are gravitationally locked in stable positions ahead and behind the planet. If TWA-7b has something similar, something astronomers are calling a Trojan disk, then it would be the first hint of this phenomenon ever observed outside our solar system. That alone would be a major discovery on top of the already major discovery of the planet itself. Now, you might be wondering, why does any of this matter? Why should you, sitting wherever you are, care about a Saturn-mass planet orbiting a dim red dwarf star 111 light-years away in a constellation most people have never heard of? Let me tell you exactly why this matters, and I promise it will hit you hard. Humanity has been searching for other worlds for centuries. Galileo pointed his primitive telescope at the sky in the early 1600s and saw the moons of Jupiter and understood that other worlds exist beyond ours. Astronomers in the 1990s proved that planets orbit other stars, and then for decades we found thousands of them, one shadow at a time, one flicker of starlight at a time. But we could not see them. We were like a detective who knows a suspect exists but has never been able to see their face. We knew other worlds were out there. We just could not look at them directly. What Webb has now demonstrated is that we can. We can point a telescope at a nearby star, block out the starlight, and actually photograph a planet. Not a gas giant the size of 4 Jupiters. Not a massive world that is almost a star itself. Planet with a mass of Saturn. That is a real planet. That is a planet in the same size category as worlds in our own solar system. And if we can photograph a Saturn-mass planet today, then the next question becomes obvious. When can we photograph a smaller one? Dr. Lagrange, the lead scientist on this discovery, has spoken publicly about her dream of eventually finding Earth-like planets this way, directly imaged, photographed, seen. The pathway to that goal is now clearer than it has ever been. Webb has shown that direct imaging at this scale is possible. Every future observation now builds on this foundation. Scientists now know which techniques work, which instruments perform as expected, and how to process the resulting data. The learning curve has been climbed. The method is proven. Looking ahead, the picture gets even more exciting. Astronomers expect that Webb will continue pushing the boundaries, potentially imaging planets even smaller and less massive than TWA-7b in the coming years. But the ultimate goal of capturing a direct image of a truly Earth-like planet is going to require more power than even Webb can provide. That is where the extremely large telescope comes in. Currently under construction on a mountaintop in the Atacama Desert of Chile, the ELT has a primary mirror 39 across, making it by far the largest optical telescope ever built. It is scheduled to come online around 2028 and is specifically designed to push direct imaging to the limit. The combination of Webb in space and ELT on the ground could, within the next decade, give us actual photographs of potentially habitable worlds. And Webb itself is not done pushing boundaries. Since it began operations in 2022, it has been relentlessly expanding our understanding of the universe. It has already helped discover more than 100 exoplanets through the transit method, where it watches stars for the brief dimming caused by a planet passing in front. It has sniffed the atmospheres of exoplanets and detected molecules like carbon dioxide, water vapor, and methane. It has found signals in the atmosphere of a distant world called K2-18b that some scientists believe could be consistent with biological processes. Though that interpretation remains under active investigation and debate, it has peered back to the very first galaxies that formed after the Big Bang. It has revealed hidden star-forming regions with unprecedented clarity. Every single month brings new revelations from this telescope. But what TWA-7b represents is something different and special even within that extraordinary track record. Because this is the first time Webb went looking for a planet on its own terms through direct imaging, found one nobody had ever seen before, and photographed it. That is a complete mission in itself. That is a triumph at every single level. Prediction, observation, confirmation, and publication, all working together perfectly. There is something deeply human about this achievement that I want you to sit with for a moment. Think about what an image is. An image is light that traveled from somewhere, entered a lens, and was captured. When you take a photograph of someone, the light that reflects off their face travels into your camera. When you look at a sunset, the light from the sun enters your eyes. The act of seeing, the act of capturing an image, is the act of receiving light from something that exists. The image of TWA-7b contains light, infrared light, beyond what human eyes can detect, but light nonetheless. The light left the planet TWA-7b and traveled through 111 light-years of space, through the void between the stars for 111 years. Light-years are not time, they are distance, but the light in that image has been traveling across the cosmos for a period that dwarfs entire human civilizations. It left TWA-7b long before the Wright brothers flew the first airplane, before the telephone was invented, before electricity lit up our cities. That ancient light from a world that is not ours entered the golden mirror of the James Webb Space Telescope, was processed, cleaned, enhanced, and is now sitting in scientific data files, ready to be studied by generations of astronomers. That is almost too poetic to be real, but it is completely real. And here is the thing that gets me most. TWA-7b is not a special planet. It is not the most exciting planet imaginable. It is not in the habitable zone of its star. It is not a rocky world that could support life. It is a cold gas planet sitting far out in the debris disk of a young red dwarf. Scientists chose to image it not because of what it is, but because of where it is and how it proved a point about planetary formation. TWA-7b is the practice run. TWA-7b is the proof that the method works. TWA-7b is the opening act. If we can photograph this planet with these instruments using this technique, then the roadmap to photographing a truly Earth-like world in the habitable zone of a nearby star becomes something we can actually plan. Astronomers can now look at the technique, look at the instruments, look at the data, and calculate what modifications and improvements would allow them to push to smaller, cooler, dimmer planets. They can write the proposal for the next telescope, the next instrument, the next mission, based on real data from a real success. That is how science builds on itself. One discovery, one confirmation, one photograph at a time. The universe is approximately 93 billion light-years across in the observable region alone. It contains an estimated 2 trillion galaxies. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. And the latest estimates suggest that most of those stars have at least one planet. Do the math if you can. The number of worlds out there is essentially beyond human comprehension. For most of human history, we had no idea any of those worlds existed. Then we found shadows and flickering light and proved they were real. And now, with the Golden Telescope floating 1,000,000 miles from Earth, we are starting to see them. Not as shadows, not as data points, as actual images, actual photographs of actual worlds. TWA-7b is the first direct image discovery of a planet by the James Webb Space Telescope. That sentence is going to be in textbooks. It is going to be in the history of astronomy forever. School children will read about this discovery the way we read about the discovery of the first exoplanets in the 1990s. And when those school children grow up, some of them will be operating the telescopes that finally photographed the first genuinely Earth-like world around a nearby star. They will build on the foundation that Anne-Marie Lagrange and her team laid down in the data of that faint orange dot sitting in the gap of a debris disk 111 light-years away. We are not alone in having planets. The universe is full of them, full of worlds with their own stories, their own histories, their own physical processes that we do not yet understand. And one photograph at a time, we are starting to read those stories. The James Webb Space Telescope just turned a new page. And what is written on the pages ahead of us is going to be the most extraordinary story humanity has ever had the privilege of discovering. The first real image of another world has been taken. And what comes next is going to change everything. Let us pull back even further because there's one more layer to this story that most people are not talking about, and it might be the most profound part of all. Every time in history that humanity has looked at the sky with a new, more powerful instrument, we have been shocked by what we found. When Galileo first looked through his telescope in 1609, He saw the moons of Jupiter and realized that not everything in the cosmos orbits the Earth. That single observation shattered the dominant worldview of his era. When Edwin Hubble looked through the 100-inch telescope at Mount Wilson in 1923, he proved that the fuzzy smudges people had dismissed as nearby gas clouds were actually entire galaxies, each containing hundreds of billions of stars, each billions of light-years away. That single discovery expanded the known size of the universe by a factor that is almost impossible to express. And when the Hubble Space Telescope launched in 1990 and began sending back images of deep space, it found that even small patches of sky that looked completely empty to ground-based telescopes were actually filled with thousands of galaxies, each older and more distant than the last. Every new telescope has done the same thing. It has taken what we thought we understood and revealed that reality is vastly, incomprehensibly bigger and stranger than we imagined. James Webb is doing this again right now in real time in our lifetime. The telescope launched on Christmas Day 2021. It spent 6 months deploying its golden mirror and cooling its instruments to the right temperatures. It released its first full-color science images in July 2022, and those images immediately broke the internet. Stars forming inside nebulae, galaxy clusters bending light from objects billions of light-years behind them. The deepest infrared image of the universe ever taken, showing galaxies from when the cosmos was only hundreds of millions of years old, still in the chaos of its early formation. People who had spent their careers in astronomy were visibly emotional looking at those early images. The telescope had exceeded every expectation. And then Webb got to work. Month after month, discovery after discovery. It detected carbon dioxide in the atmosphere of a planet 700 light-years away, the first time that molecule had ever been detected in an exoplanet atmosphere. It found water and sulfur dioxide in other atmospheric studies. It found methane and carbon dioxide together on the ocean world K2-18b, which sparked a cautious but genuinely exciting conversation in the scientific community about the possibility of a biological source. Though scientists are careful to note that non-biological explanations remain entirely possible and further observation is needed. What Webb did with TWA-7b represents a completely different capability unlocked by this telescope. Not sniffing the chemistry of a planet as its light passes through its atmosphere during a transit, but actually seeing the planet, seeing its own light, seeing it sitting there in space glowing faintly in the infrared orbiting its star. The difference between these two methods is enormous. Transit spectroscopy, where you analyze starlight filtered through a planet's atmosphere, tells you what chemicals might be in that atmosphere. Direct imaging, what Webb just did with TWA-7b, tells you where the planet is, how it is moving, what it looks like as a distinct object in space. And most importantly, direct imaging opens possibility of studying planets that do not happen to pass directly between us and their star. Most planets do not transit. Most planets from our angle of view never pass in front of their star at all. Direct imaging has no such limitation. If the planet is bright enough and the coronagraph is powerful enough, it can be seen regardless of where it is in its orbit. That is a staggering expansion of what we can study. Right now, even as you are watching this, the Webb telescope is pointed somewhere in the sky gathering photons, building up images of things we've never seen before. The data is being transmitted back to Earth in compressed digital streams and processed by teams of scientists around the world. Somewhere in that incoming data, there may be the next TWA-7b or something.